Hi, my name is Sivraj, son of S. Krishnamurthy, and my matric number is B1224100721. So today I would like to present our project for BERT3414 RF Technique and Microwave. So our project is titled Design of Low Pass Filter and Band Pass Filter using the insertion loss method. Our project is, during this presentation, I would like to explain the theory, design process, simulation, results, discussion, and conclusion of our project. So let's move on. Okay. So before starting the design, we determined the specification of the low pass filter. So the low pass filter was designed with a cutoff frequency of 1.8 GHz, 30 dB attenuation of at 4.9 GHz, and 3 dB Chebyshev equal ripple response. So based on the attenuation curve, we selected a third order filter, which provides a good balance between filter performance and filter circuit complexity. Okay. So here are the calculations that we made for it. Okay, and here this slide shows the normalized low pass filter prototype, and we selected the T network topology instead of the pi network because it provides the lower insertion loss and better performance when implemented using the distributed microstrip transmission line. And the prototype also consists of alternating series inductors and also shunt capacitors. So as we can see here, we can see the calculation for the series inductors and shunt capacitors. And from the Chebyshev prototype table, the values obtained are G1 is equals to 3.3487, G2 0.7117, G3 is 3.3487, and G4 is 1. So we just need to substitute all here at the given formulas. Okay, so the next one is Richard transform. Since lump inductors and capacitors are not suitable at the microwave frequencies, we apply the Richard transformation. So this transformation converts the lump inductors and capacitors into the quarter wavelength transmission line stubs, and it allows the filter to be implemented using the microstrip transmission lines, which perform much better at the higher frequencies. Okay. So after this, we will proceed with the Kuroda identity. So yeah, after the Richard transformation, the circuit still contain the series stubs that are difficult to fabricate on a PCB. So therefore, we apply the Kuroda's identity. And here it converts the impractical series stub into the parallel open circuit shunt stub by introducing the unit elements. So as you can see here, here are the formula. Z1 new equals to n square times Z1. Here Z2 new equals to n square times Z2. Okay, so before that we need to find the n square. Here are the given formula for the n square. Okay, so this transformation makes the distributed filter practical for PCB fabrication and eliminates all the needed for grounding wires. So as you can see here, after the Kuroda identity calculation, I did sketch a circuit. Okay, sorry. Okay, so here, okay, the next part is denormalization. So after obtaining the normalized transmission line impedance, here as you can see, we perform the denormalization using a 50 ohm reference impedance. So to obtain this, we need to multiply all the given values with the 50 ohm. Okay, so this convert the normalized value into the practical characteristic impedance that required for microstrip implementation. And the calculated impedance are then used in the ADS to generate the physical dimension of the microstrip line. Okay, so after calculating all it, we need to substitute into the circuit transmission lines. Okay. Okay, so the next part is microstrip layout. So this slide shows the microstrip layout generated using the ADS. And the layout was synthesized using an FR4 that subtracts with dielectric constant of 4.7, thickness of 1.6 millimeters, copper thickness of 35 micrometers. Okay, and all the transmission lines have an electrical length of 45 degree, while the widths corresponding to the calculated characteristic impedance. Okay, so this, okay, the next one is this is the initial ADS schematic before the optimization. Okay, before I did the tuning, here are the circuits. So the distributed low pass filter was constructed using the MLIN transmission lines, MLOC open stub, MPEE junction, 50 ohm ports as parameter simulation block. And at this stage, the circuit still suffered from the parasitic effects and did not fully satisfy the design requirements. So here the schematic after the tuning. To improve the filter performance, we use the ADS tuning feature, and only the length of the transmission lines and open stubs they are adjusted while maintaining their characteristic impedance. So this compensates for discontinuities, freezing fields, and subtract the losses. Okay. Okay. This graph compares the frequency response before and after tuning. And before tuning, the insertion loss at 4.9 GHz was only at 27.278 dB, which failed to meet the required 30 dB attenuation. After the tuning, as you can see here, the insertion loss improved to 30.032 dB at the cutoff frequency of 1.8 GHz, and the insertion loss was only 0.429 dB. So it shows the excellent transmission performance. And here, this confirms that the ADS optimization was successfully made all the design specifications. Okay. Okay. Here the last part for the low pass filter. This figure out the final physical microchip layout. So the wide open stub acts as a shunt capacitors, while the narrow transmission line here, it represents the high impedance unit elements, and this layout can be directly fabricated on a PCB. Okay, so that's all for the low pass filter. Thank you.
Band pass filter. The filter was designed with center frequency of 1.8 GHz, bandwidth of 180 MHz, fifth order Chebyshev equal ripple response. Unlike the LPF, the band pass filter uses only lumped components. This figure shows how the low pass filter prototype is transformed into a band pass filter. The upper circuit is the normalized low pass prototype, while the lower circuit is the resulting band pass prototype. During the transformation, each series inductor becomes a series LC resonator, and each shunt capacitor becomes a parallel LC resonator. These resonators are designed to operate at a center frequency of 1.8 GHz with a bandwidth of 180 MHz, allowing only the desired frequency range to pass while rejecting unwanted frequencies. This slide presents the calculation of the bandpass filter components. Using the low-pass prototype values and the bandpass transformation equations, we calculated the inductance and capacitance for both the parallel and series resonators. The calculated values include L1 and L5 of 0.127 nanohenry, C1 and C5 of 61.57 picofarad, L2 and L4 of 33.68 nanohenry, and C2 and C4 of 0.232 picofarad. These values were then implemented in ADS to construct and simulate the final bandpass filter. This slide shows the completed fifth order bandpass filter circuit after replacing the prototype elements with the calculated inductors and the capacitors. The circuit consists of alternating series and parallel LC resonators connected between 50 ohm source and load impedances. These resonators allow frequencies around the center frequency of 1.8 GHz to pass while rejecting frequencies outside the desired bandwidth. This theoretical circuit is then implemented in ADS for simulation and performance verification. This slide shows the completed ADS schematic for the bandpass filter. The circuit consists of 3 parallel resonators, 2 series resonators, input and output ports as parameter simulation controller. The simulation was performed between 1 GHz and 2.6 GHz. The simulation shows that the bandpass filter operates exactly as required. The bandpass extends from 1.710 GHz to 1.890 GHz, producing the required 180 MHz bandwidth. The return loss is below negative 10 dB, indicating good impedance matching, while the insertion loss remains very low across the passband. From the results, we conclude that the design successfully achieved all technical specifications. The ADS tuning improved the low-pass filter attenuation from negative 27.278 dB to negative 30.032 dB while maintaining a low insertion loss of negative 0.429 dB. Richest transformation and Kuroda's identity enabled the practical implementation of the distributed filter. In addition, using distributed microstrip technology, reduced PCB complexity, minimized material waste, lowered power consumption, and supported environmentally sustainable engineering. In conclusion, we successfully designed and simulated both the distributed low-pass filter and the lumped bandpass filter using the insertion loss method. The application of Richard's transformation, Kuroda's identity, and ADS optimization enabled us to meet all the required design specifications. This project demonstrated how theoretical microwave filter design can be translated into a practical and efficient RF circuit suitable for the real-world implementation while supporting sustainable engineering practices. Thank you.